Hey all, it's great to be here. Thank you so much for joining. I'm excited, I'm humbled to be speaking to all of you, and I get to talk about one of my favorite topics, something that's very near and dear to my heart, resilience engineering. Now, the field of resilience engineering is pretty wide, and there are a lot of ways into it. For my part, I started doing facilitation of retrospectives, and deeper into it, I want to understand what it meant to be safe, what human factors meant to system development engineering. As part of that, we typically assign blame awareness to our postmortems, retrospectives, and such. And now, while our talk today is myth busting, I'm going to keep that in mind. We're not here to blame people. We're not here to throw people under the bus. We're here to learn, and so we're looking for best intent on how we can move forward and how we can improve our systems. Now, resilience engineering seems like a topic that came from software industry. Resilience and engineering seem like core parts. But it's only been a short time we've really had a hand on that ball. The topic of resilience engineering has come into light from a lot of other industries, namely nuclear power safety, transportation, medicine. And so there's something very specific in mind when we say resilience engineering. So let's talk about a definition. Resilience is the expression of how people, alone or together, cope. An organization's performance can be said to be resilient if it can function as required under expected and unexpected conditions alike. Now, this is a very solid definition. There's a lot to take in here. But it's also a little bit verbose. It's hard to think about what part of our systems are actually resilient, what aren't, when we're trying to keep this long definition in mind. I'm putting together this talk, and I still need to read off the slide for it. So we're thinking about resilience in our systems. A shorthand for it might be, can it adapt? And when we're saying something can adapt, the idea is, can it make decisions? And we're talking about decisions that does not include things like conditional logic. We're asking, can it change the course? Or, in the process of looking at our systems and our environment, can it stay the course, believing that's still the right way forward? Can it rely on hints, clues, assumptions, and any expertise it's built along the way to plot a path forward? Only with this can we say something is displaying resilience. And so with that, let's talk about our first myth. Myth number one. We're building resilience into our software and server architecture. This is impossible. It's because our servers and our softwares cannot make decisions. When we say this, we probably mean robustness or maybe reliability. Our code cannot build expertise. Our software cannot make judgment calls. That we can only do what we've determined beforehand it needs to do and what we expect it to do. So if a software as a service company says, we've got this great product, we're going to add resilience to your company, they're probably trying to sell you something. So with that in mind, let's talk about those three definitions and break them down a bit more. Often we're thinking about robustness when we're talking about our software or our servers. Robustness means, can the system perform with predetermined expectations of those boundaries? When we say this, we probably mean things like, can we add static caching on our site? Can we do things like add automatic failover of our databases? Can we apply load balancers that add or remove nodes when needed? If there's more load or perhaps a node fails out, its health check fails. Understanding this difference between resilience is important. Next, let's talk about reliability, which is pretty important since we're site reliability engineers. In this context, reliability is, can we trust that the system is performing within the expected bounds? What's our assessment of those boundaries? How much faith do we have in our system to maintain what it's currently doing and if it'll break those bounds? Can we understand the limitations that we are currently working with and what will be ahead of us in the future? And finally, resilience. When we're talking about resilience, talking about going past those expected bounds. Can it adapt when it breaks those limitations? When we're in an incident and we're using our runbooks and we need to go off script, that's resilience. If we're talking about an operator who sees a rogue process on a server that's taking up resources and killing that process, that's resilience. If we're talking about escalating a page because I don't have the confidence in believing that I fully understand what's going on, I need to pull more people in to get a better assessment of my environment, that's resilience. Resilience is displayed when people are making large and small changes and our expectations around that. So while we say our servers can't display resilience, our systems can, because people are part of the system. People are what are keeping our systems up every day. And we might think, well, is this kind of pedantry? Aren't we splitting hairs here? I mean, we generally mean the same thing: resilience, robustness, reliability. We want to keep our sites up and available. But there's an important distinction between these, and there's a reason we separate these out. Our chaos engineering experiments aren't as effective if we're not finding the deep insights, if we're not focusing on resilience. Our incidents are inflexible and brittle if we're not focusing on how we can adapt during crisis mode. Our retrospectives are shallow when we're searching for data. We're trying to understand the problems that are happening within our system. Without an understanding of these concepts, our systems are brittle. Next myth. Complexity is the enemy of a well-maintained system. Now this seems very intuitive. We want to reduce complexity. It's hard understanding our systems. If we can simplify it, we'll have an easier time. But there's good reason we build complexity into our systems. When we're adding functionality, that's adding complexity. Our demands require complexity to be added to our system. And so the question isn't always, how can we simplify our systems? The question we should be asking ourselves is, how do we cope with the necessary complexity that is built within our systems? What do we do when the requirements in front of us say, we need to add more functionality, and therefore this system is going to be more complex? And there are two views on this. The pessimistic view is that we start with this building an expansion. We're constantly looking to make our systems better, faster, stronger. How can we reduce the costs built within it? Until we get to this saturation point, and our systems can no longer take anymore. And at that point, we face a collapse. And again, this seems very intuitive. If you ever worked with any kind of heavy code base, it's like, well, this is a mess. We need to dump this and write this over again. This is too complex. We can't handle this anymore. Maybe we're adding so many dashboards from so many incidents. I don't know where to start when we're trying to investigate. Or we're adding pages, and I'm getting paged multiple times a night. And so we're adding to our systems. Resilience engineering, though, takes a different tact. Resilience engineering believes in the optimistic view. Since we are people within the system, and we can modify our system, we can also self-monitor it. We can understand what's going on within our system before it collapses. We can adapt, we can see what's happening down the road and make changes to prevent that failure state. Now, resilience engineering is a continuous effort. We need to be constantly doing this. We don't know when we're going to fail. We don't know when the failures are before we can jump ahead of them. It's an investment, and not all those investments are going to necessarily pay off. Sometimes they're very costly, but they're critical to avoid that collapse in the pessimistic view. Next myth. We need to execute chaos engineering experiments to find the bugs. And you'll see this often when we're talking about chaos engineering, that we're going to go start unplugging things in the data center. We're going to pull out some plugs, we're going to inject chaos into our systems and see where the bugs are. I'm going to fix them, and our systems are going to be safe. And that's not the point of chaos engineering experiments. We're looking to develop expertise. We're looking to develop understanding of our system. What are these assumptions that we have about our system, and how can we challenge them? We test those assumptions, and they're wrong, we've learned something, we spread expertise throughout our organization. Also, chaos engineering is not about injecting chaos. The chaos is already there. We're trying to find it. So when we're talking about chaos engineering, what we're really looking to do is develop intuition. How is it that our best engineers seem to know what's going on before we do, before a bug hits, before a failure hits, and to make the right call? That's what we're looking to do with chaos engineering. For chaos engineering to work, we need to understand our system. Myth number 4, always follow best practices to ensure system availability. And again, this feels like very intuitive. They're best practices, they're the best, and they're practiced. We should do them. But best practices will sometimes lead us astray. Systems will fail for all sorts of reasons. When we go in and we think we're doing the right thing, we're following best practices, and sometimes our systems will still fail. It's often with hand waving too when we cite best practices. I read a blog post, I saw a tweet, saw someone at a conference, and we want to bring that here. But best practices don't always apply 100%. They don't map one-to-one to organizations. Should we deploy on a Friday? Most of the time we say no. That's a best practice. Never, ever deploy on a Friday. There are engineers who are on call. We don't want to disrupt their work-life balance. We make sure they get a restful weekend. We don't want to do anything risky. Unless we just noticed a bug an hour before quitting time. Or maybe we need to run an experiment over a weekend because of different traffic patterns. Or maybe there's a release happening the weekend, some event, and we need to be prepared for that. And so while we can say that, yes, avoiding deploys on a Friday is a best practice, there are times we need to ignore best practices. And therefore, calling things best practices is a misnomer. The same applies to runbooks and guides and wikis, and sometimes our past judgment. Just because something worked in the past does not guarantee it's going to work again in the future. Best practices do not guarantee safe actions. There is no guarantee if you do this thing, it will work for certain. We may come across a best practice in our day-to-day work and say, okay, we're in an incident, I should probably wait for the tests to pass before deploying. That is a best practice. Say your site is down already. Should you wait for the tests? Should you give your site more downtime to make sure your new change? Maybe. That's a judgment call. How long will the test take? How big is the outage? How long have we already been waiting? What's the customer impact? We don't know. But waiting for tests to pass before deploying is a best practice. What happens if we disregard a best practice and it works out right? Was that the correct risk to take? Say we ignore a best practice and it goes wrong. Is that still the right path? We don't know until afterwards. We're constructing these events after the fact. Our judgment calls are after the events. And so when we talk about best practices, it's an easy way to be blameful after something goes wrong. Why'd you do that? You should have followed best practice. Myth number 5, effective retrospectives require actionable items to follow up. I see this in a lot of retrospective templates that here's the time it started, here's what it ended. Here's the things we're going to do to make sure this never happens again. Retrospectives are a time for learning. That's what we're there for. We're looking to share knowledge and share expertise. And we need to develop an understanding of the problems in front of us. Retrospectives should also be transparent and open to anyone who wants to attend, even if it's not their stack or they're part of the org. They might learn something. They might ask the right questions that the experts believe everyone else to know. It's tempting to think we can graph everything after an incident. We're going to put a page on that. We're going to put a guardrail. Here's a dashboard. We're going to make sure this never, ever happens again. And I see this associated a lot with retrospective templates that have root cause as part of the template itself. And it makes sense. We want answers. We want to know that this will never happen again. What are the things we're going to do to prevent that? But if we're not using actionable items after the fact, How do we know our retrospectives are even effective? How do we know that getting in a room for an hour, the interviews we're having, are worthwhile? And this is hard to judge. We're basically saying, we're going to gather in a room, we're going to try to learn stuff. How much have we leveled up as an organization because of that meeting? And learning happens gradually over time in small increments, and it's almost invisible in a short time period. An alternate question might be, how much we gain from being at a conference, say? Are there actionable items for being at SREcon? I mean, our companies are paying for our flights, the ticket, the hotel room, maybe food budgets, any kind of incidentals. But we still come to SREcon because we believe it's valuable. We come back with lots of learning. We bring it back to our org. Maybe we have documents we bring to people. We spread that knowledge. And that's important. I think we should take that same philosophy and apply that to our retrospectives. Myth number 6, root cause. There's no sentence around this, just root cause in general is a myth. Root cause does not exist. And before you say it, root cause is plural, also does not exist. And I see this often with retrospectives. We want to know what happened. Let's assign it to this one thing. We have this complex problem in our complex system. Can't something just be simple? Here's the one thing. If we solve this one thing in front of us, we make sure this never happens again, we'll never have an outage. It'll be great. But retrospectives that highlight root cause often lead to shallow answers. And we also lead to misattributing where the blame is. We tend to assign root cause to any place that's politically convenient. People who are on the sharp end, as they say. And with any kind of minimal effort, we can probably find a root cause to the root cause. What came before that? And what came before that? And what came before that? And so it's root cause all the way down. I also see the 5 whys applied to a lot of retrospectives as a guide to how we should figure out what happened. And this is equally fallacious. For those who aren't familiar with it, the 5 whys says you have a problem, why did that happen? And we come to something before that. Well, why did that happen? We come to something before that. And we ask 5 whys deep until we have a quote unquote deep enough answer. And this has the same problem with root cause. This has an expectation of linear causality, that one event always follows another, which follows another, which follows another. And that's not the case. This ignores a concept called emergent phenomena, the idea that many agents in a system contribute to what happens next. No single agent can be responsible, but multiple agents together contribute to it. Ask your team individually to come up with their own set of 5 whys and watch them each come up with their own list of what happened, which just goes to show that we are setting up the construction of the events after the fact. We're deciding the events ourselves that make sense to our worldview. We never talk also about the root cause of success. What makes something work? What's the one thing that went right that allowed everything else to work for it? Because many things happen. Next, we're going to talk about replacing root cause with contributing factors. It's an easy substitution, maybe an extra syllable or two, but it highlights exactly what you want to be thinking about. There are many things happening. They're adding to the event. We're understanding this together, and we also can acknowledge that it's not the end. We have to stop somewhere. We only have so much time and so much energy to devote to our understanding of problems. But we're not saying it's the end there, it's not the root of the problem. This also allows people to get leveled up faster. We can say, how are things contributing to it? What's your understanding of the problem? What's your worldview at the time, beyond a single event or a single agent? Myth number 7, the frequency and severity of incidents are good indicators of how safe we are. I often see that we're using things like mean time to recovery or mean time between failures as an indication of how safe our system is. But the recency, frequency, and severity are including many things. For starters, failures are constantly happening within our system. We might not acknowledge them, because they're so low level we don't think they're worthy, or maybe the robustness of our system is handling them, but they're there. This also ignores a concept called dark debt. Now, we've probably heard the term technical debt, where we make decisions and later down the road we need to pay for it. Time, energy, code rewrites, etc. But with dark debt, we don't know that exists. We're making decisions and we don't know when or where we're going to have to pay that off. So when we're talking about between incidents or how long it's been since our last outage, we don't actually know about that dark debt and we're ignoring it because we assume our systems are safe. Severity and numbers like this can be gamed. Maybe this interval, we've had a lot of Sev 1s, so we're going to call this next incident a Sev 2 just so it looks like we're doing our job. Or maybe we want to bump this up because I want to get this done. I want to put some resources on this. I want to fly this up to top management so they know this is an important thing. We need to put some resources. We need to put this on our roadmap. Who recognizes these logos? Yeah. This is a fun bug to trip over last year, or two, I should say. These are the Meltdown and Spectre logos for the incidents that happened last year. The idea was that there was code written in the 90s that allowed for speculative execution of code on hardware. Now, the engineers that wrote this code went through all the proper channels. They were experienced, they had tests, they had code reviews. It was in production for decades before it was discovered. How safe were we before we discovered Meltdown and Spectre? We would have said we're very safe. It's been decades since in production. It seems to work for us. And how much did our systems require our adapting? How much work did we have to do to escalate this problem, to make changes in our systems? The day after, the entire internet went, okay, we need to reboot our servers. We need to pull in these patches. Only with our knowledge do we understand how safe our systems actually were. So how long should it be before our code is considered safe when it's in production? I certainly don't have code that's written 5 years ago that's still in production, let alone 25 years old. How many of our engineers in this room, senior, smart engineers, were born after this code was written? Think about that. That scares me. I'll never know if my code is 100% safe. And I need to live in that. That's okay. We need to understand that the frequency between failures is not indicative of how safe it is. So instead of sharing numbers, we need to share expertise. Get your experts to talk about how confident they are in the system. What scares you about the system? Where do we need to put efforts? Where do you think, being on the sharp end, that the next problem will happen? Next myth. Our worst incidents produce the greatest learning. It's fun to talk about war stories. It's fun to talk about this major outage and how it was a complicated system and what happened in the events that unfolded and how we remediated. And those are good to talk about. Those are important to talk about. But that does not map one-to-one, does not scale with how much learning is involved with the incident. Sometimes we learn a lot from small incidents. And sometimes, we can fail to outcome bias because of this. Well, if it was a major incident, then there must have been major decisions that happened to let this occur. What were the major decisions? What did we do that was so critical that caused this large outage? And that's not necessarily true. Even in the most blame-aware organizations, there is a tendency to smooth out the rough edges when something bad happens. Maybe you don't want to name names because you don't want to feel like you're the person putting someone else on the spot because of that. This is so bad, I don't want them to get fired because of this, so maybe I'll just say something happened, someone made a command change, someone might have rolled over the database, etc. Instead, we should be looking to the normal, everyday work. What about the close calls we're making? What about the ways we're preventing our systems to fail? Investigate those. That's where the experts are making the decisions that are important. Myth number 9, error budgets can be used to control risk. This is absolutely the wrong conference and the wrong room to have this slide. And I'll be transparent. I'm not a huge fan of error budgets. but I know they're important to SRE culture. And I know a lot of people have had effective use of error budgets. I don't want this part of the talk to be, don't use error budgets. That's not what I'm saying. We can have that argument outside, you can yell at me in person. What I will say is, if we're going to use error budgets, we need to understand what we're doing with them and what they can actually produce for us. And controlling risk is not one of them. Quick story. An engineer is hired. They're a senior engineer. They are boot camping, rotating with different teams as they start. One team, they're making some code changes. The code changes got peer review. They run the test locally in dev. They go through staging. Other engineers in staging look at it, looks fine. It runs through smoker tests. It goes into prod. 2 minutes later, the site is down. And it's correlating pretty strongly with this deploy. So we're looking through the change sets, seeing what might have caused it. Apache instances just won't stay up. They fall down after a minute or two. Keep rebooting. Eventually, revert the code, reboot the Apache instances, site stays up. Investigation shows this new engineer made a code change that broke the site. Now, what if I told you that code change was deleting a CSS file? A CSS file took down a major site. They went through all the proper channels, they did everything they were supposed to do, and yet there was an outage. The 404 page was depending on the CSS file. And when naturally in production there was a 404, it tried to include that file. The static assets weren't built for it, and so there was another 404. And that 404 page generated another one until they blocked all the child workers and Apache went down. Where is the risk in this? At one point, was the engineer doing something risky? Where's the control for this? Are all deploys risky? Is there some level of risk in it? When should we be risky? When are we getting good at doing risky things? That's what we need to focus on. Get good when risk needs to be done, when we have to make risky changes. There's an idea in resilience engineering of safety 1 versus safety 2. Error budgets take a very safety 1 approach. We're going to protect our system, we're going to look at failures, make sure they don't happen again. Resilience engineering says, yes, and. Let's also look at what went right. What are the proactive things we can do to make sure our systems don't fail when we're doing things right? What are we doing every day to make sure our systems stay up? We don't know much about our system by counting the number of errors, and we can't calculate the risk just by those errors. Myth number 10. The field of resilience engineering is representative for the study of human factors. Chances are, if you hear anyone speaking about resilience engineering, they look like me. They're probably white, they're probably male, they're probably from the US, maybe Canada or Europe, and that sucks. We're supposed to be looking into how humans make decisions. And when we have a small subset of people doing that investigation, we're failing. This is a major failure on our part. I want to be self-reflective on this. And as an industry, as a field, we need to be more reflective of this. So what I will say is we need to encourage more people to get into resilience engineering. Find us. We have the same attitude towards blame awareness as you would in postmortems or retrospectives. Find us. We'd love to talk to you. So let's talk about some takeaways as we end here today. For starters, here are some great materials to do further investigation. The first one is called the Edo principle. It's how we made trade-offs in production, the efficiency thoroughness trade-off. It's a great book, give you a deep understanding of how we make these decisions. The second is a paper by Dr. Cook, How Complex Systems Fail. It's 4 pages, you can find it online. You'd swear he wrote that for software engineering. The last is Field Guide to Understanding Human Error. That should be required reading for retrospectives. You can't plan for everything. We need to get good at preparing for the unknown. Get experts to share their expertise. That's the only way we're going to be getting good at displaying resilience in our systems. And finally, embrace uncertainty, because that is the only way we can look forward. The chaos is there. We need to look into it and get used to it, because there's no other choice around that. I want to thank especially Nora Jones, Dr. Richard Cook, and Allspa. They were hugely influential in this talk, reviewing slides, helped me gather information. Please come talk to me. I'll be around in the end if you want to talk more about this. When you yell at me about error budgets, it'd be great. I'd love to talk to you. Thank you.